Carbon steel is steel in which the main interstitial alloying constituent is carbon in the range of 0.12 to 2.0%. The American Iron and Steel Institute definition says, steel is considered to be carbon steel when no minimum content is specified are required for chromium, cobalt, molybdenum, nickel, niobium, titanium, tungsten, vanadium, zirconium, or any other element to be added to obtain a desired alloying effect. When the specified minimum for copper does not exceed 0.40%, or when the maximum content specified for any of the following elements does not exceed the percentages noted: manganese 1.65, silicon 0.60, copper 0.60. The term carbon steel may also be used in reference to steel which is not stainless steel. In this use, carbon steel may include alloy steels. As the carbon percentage content rises, steel has the ability to become harder and stronger through heat treating. However, it becomes less ductile. Regardless of the heat treatment, a higher carbon content reduces weldability. In carbon steels, the higher carbon content lowers the melting point. Type: mild and low carbon steel. Mild steel, also known as plain carbon steel, is now the most common form of steel because its price is relatively low while it provides material properties that are acceptable for many applications. Low carbon steel contains approximately 0.05 to 0.25% carbon, making it malleable and ductile. Mild steel has a relatively low tensile strength, but it is cheap and easy to form. Surface hardness can be increased through carburizing. It is often used when large quantities of steel are needed, for example as structural steel. The density of mild steel is approximately 7.85 grams per cc and the Young's modulus is 200 gigapascals. Low carbon steels suffer from yield point run-out where the material has two yield points. The first yield point is higher than the second and the yield drops dramatically after the upper yield point. If a low carbon steel is only stressed to some point between the upper and lower yield point, then the surface develop Luder bands. Low carbon steels contain less carbon than other steels and are easier to cold form, making them easier to handle. Higher carbon steels. Carbon steels which can successfully undergo heat treatment have a carbon content in the range of 0.30 to 1.70% by weight. Trace impurities of various other elements can have a significant effect on the quality of the resulting steel. Trace amounts of sulfur in particular make the steel red short, that is, brittle and crumbly at working temperatures. Low alloy carbon steel, such as A36 grade, contains about 0.05% sulfur and melts around 1426 to 1538 degrees Celsius. Manganese is often added to improve the hardenability of low-carbon steels. These additions turn the material into a low-alloy steel by some definitions, but AISI's definition of carbon steel allows up to 1.65% manganese by weight. Types. Carbon steel is broken down into four classes based on carbon content. Low carbon steel up to 0.3% carbon content. Medium carbon steel, approximately 0.3 to 0.6% carbon content. Balances ductility and strength and has good wear resistance, used for large parts, forging and automotive components. High carbon steel, approximately 0.6 to 1.0% carbon content. Very strong, used for springs, swords, and high-strength wires. Ultra-high carbon steel, approximately 1.25 to 2.0% carbon content. Steels that can be tempered to great hardness. used for special purposes like knives, axles or punches. Most steels with more than 2.5% carbon content are made using powder metallurgy. Heat treatment. The purpose of heat treating carbon steel is to change the mechanical properties of steel, usually ductility, hardness, yield strength, or impact resistance. Note that the electrical and thermal conductivity are only slightly altered. As with most strengthening techniques for steel, Young's modulus is unaffected. All treatments of steel trade ductility for increased strength and vice versa. Iron has a higher solubility for carbon in the austenite phase. Therefore, all heat treatments, except spheroidizing and process annealing, start by heating the steel to a temperature at which the austenitic phase can exist. The steel is then quenched at a high rate, causing cementite to precipitate and finally the remaining pure iron to solidify. The rate at which the steel is cooled through the eutectoid temperature affects the rate at which carbon diffuses out of austenite and forms cementite. Generally speaking, cooling swiftly will leave iron carbide finely dispersed and produce a fine-grained pearlite, and cooling slowly will give a coarser pearlite. Cooling a hypoeutectoid steel results in a lamellopearlitic structure of iron carbide layers with alpha ferrite between. If it is hypereutectoid steel, then the structure is full pearlite with small grains of cementite scattered throughout. The relative amounts of constituents are found using the lever rule. The following is a list of the types of heat treatments possible. Spheroidizing. Spheroidite forms when carbon steel is heated to approximately 700 degrees Celsius for over 30 hours. Spheroidite can form at lower temperatures, but the time needed drastically increases, as this is a diffusion-controlled process. The result is a structure of rods or spheres of cementite within primary structure. The purpose is to soften higher carbon steels and allow more formability. This is the softest and most ductile form of steel. The image to the right shows where spheroidizing usually occurs. Full annealing. Carbon steel is heated to approximately 40 degrees Celsius above AC3 or ACM for 1 hour. This ensures all the ferrite transforms into austenite. The steel must then be cooled slowly, in the realm of 20 degrees Celsius per hour. Usually it is just furnace cooled, where the furnace is turned off with the steel still inside. This results in a coarse pearlitic structure, which means the bands of pearlite are thick. Fully annealed steel is soft and ductile, with no internal stresses, which is often necessary for cost-effective forming. Only spheroidized steel is softer and more ductile. Process annealing. A process used to relieve stress in a cold-worked carbon steel with less than 0.3 Wt% C. The steel is usually heated up to 550 to 650 degrees Celsius for 1 hour, but sometimes temperatures as high as 700 degrees Celsius. The image rightward shows the area where process annealing occurs. Isothermal annealing. It is a process in which hypoeutectoid steel is heated above the upper critical temperature, and this temperature is maintained for a time, and then the temperature is brought down below lower critical temperature and is again maintained. Then finally it is cooled at room temperature. This method rids any temperature gradient. Normalizing. Carbon steel is heated to approximately 55 degrees Celsius above AC3 or ACM for 1 hour. This ensures the steel completely transforms to austenite. The steel is then air-cooled, which is a cooling rate of approximately 38 degrees Celsius per minute. This results in a fine pearlitic structure and a more uniform structure. Normalized steel has a higher strength than annealed steel. It has a relatively high strength and hardness. Quenching. Carbon steel with at least 0.4 Wt% C is heated to normalizing temperatures and then rapidly cooled in water brine. or oil to the critical temperature. The critical temperature is dependent on the carbon content, but as a general rule is lower as the carbon content increases. This results in a martensitic structure, a form of steel that possesses a supersaturated carbon content in a deformed body-centered cubic, crystalline structure, properly termed body-centered tetragonal, with much internal stress. Thus, quenched steel is extremely hard but brittle, usually too brittle for practical purposes. These internal stresses cause stress cracks on the surface. Quenched steel is approximately 3 to 4-fold harder than normalized steel. Mar-tempering is not actually a tempering procedure, hence the term mar-quenching. It is a form of isothermal heat treatment applied after an initial quench of typically in a molten salt bath at a temperature right above the martensite start temperature. At this temperature, residual stresses within the material are relieved and symbionite may be formed from the retained austenite, which did not have time to transform into anything else. In industry, this is a process used to control the ductility and hardness of a material. With longer mar-quenching, the ductility increases with a minimal loss in strength. The steel is held in this solution until the inner and outer temperatures equalize. Then the steel is cooled at a moderate speed to keep the temperature gradient minimal. Not only does this process reduce internal stresses and stress cracks, but it also increases the impact resistance. Quench and tempering. This is the most common heat treatment encountered, because the final properties can be precisely determined by the temperature and time of the tempering. Tempering involves reheating quenched steel to a temperature below the eutectoid temperature, then cooling. The elevated temperature allows very small amounts of spheroidite to form, which restores ductility, but reduces hardness. Actual temperatures and times are carefully chosen for each composition. Austempering. The austempering process is the same as mar-tempering, except the steel is held in the molten salt bath through the binite transformation temperatures, and then moderately cooled. The resulting binite steel has a greater ductility, higher impact resistance, and less distortion. The disadvantage of austempering is it can only be used on a few steels, and it requires a special salt bath. Case hardening. Case hardening processes harden only the exterior of the steel part, creating a hard, wear-resistant skin but preserving a tough and ductile interior. Carbon steels are not very hardenable, therefore thick pieces cannot be through hardened. Alloy steels have a better hardenability, so they can through harden and do not require case hardening. This property of carbon steel can be beneficial, because it gives the surface good wear characteristics but leaves the core forging temperature of steel. Bibliography. D'Agamo, E. Paul, Black, J.T. Koza, Ronald A. Materials and Processes in Manufacturing, Wiley, ISBN 0-471-65653-4. Oberg, E. A. Al. Machinery's Handbook, Industrial Press Inc., ISBN 0-8311-25993-3. Smith, William F. Hashemi, Javad, Foundations of Materials Science and Engineering, McGraw-Hill, ISBN 0-07-295358-6.